So to put everyone on the significance of these ocean moons, they were not known 27 years ago. And the only body in the known universe, basically, that was known to bear liquid water was Earth. And now we have, depending on how strict your definition is, we know at least 5 other bodies that have liquid water, and they're all icy worlds. They are all moons in the outer solar system. This is Europa. That was the first one, the first ocean world that was discovered in 98, 99. So these are the 5 generally accepted ocean worlds. 3 orbit Jupiter, Europa, Callisto, Ganymede, and Enceladus and Titan orbit the Saturn system. And there's a new kid on the block, Mimas, very likely also is an ocean world that was published half a year ago or so by an analysis of Cassini data, reanalysis of Cassini data. It's even a bit smaller than Enceladus. So yeah, the number is growing. There are candidates like Triton in the Neptune system, also a suspected ocean world, but these are the best known. So most of the liquid water in our solar system by far is in ocean moons, and it's probably also true for the universe, that most of the liquid water in the universe is in these bodies. Yeah, this is Saturn now, in this beautiful Cassini image with the sun behind the planet. In this backlight configuration, you see not just the main rings, but also these outermost diffuse E-ring, and there's a little Enceladus, like in the center of the E-ring. And this connection was known even before the Cassini spacecraft arrived, that this tiny moon, Enceladus, for some reason sits in the middle of the E-ring, but no one, or very few people actually, expected what really is the reason for this. This is the cryovolcanic activity. You see, zoom in here, you see the Enceladus in black, and this is the plume. And yes, and basically the ice grains are shot into space at such high velocities that they overcome the gravity of the small moon, and on its way around Saturn there's a track of ice grains that basically Enceladus loses all the time, and in this way the E-ring is a storage ring of material that comes from the interior of Enceladus as well. And that's, yeah, so before I come to the science, not all of you might be familiar with Enceladus, so some introduction. It's a relatively small moon, just 500 kilometers in diameter. And for an icy moon, it has a relatively high density of 1.61 gram per cubic centimeter. And that means that more than half of the moon's mass must be rocky. So it has a relatively large rocky core. The temperatures you get from sunlight at the equator at a sunny afternoon is 75 Kelvin. And at the poles, you would expect something like 50, 55 Kelvin. This is where the active region is, right? So these jets of ice particles, they penetrate the icy crust through these crustal cracks called the Tiger stripes, 4 parallel stripes, and this is an infrared picture, and this emission of matter goes along with an emission of energy and heat in the form of infrared and microwave emission. And you reach temperatures in the most active hotspots here of almost 200 Kelvin. So it's about almost 150 Kelvin above the ambient temperature. So it's really hot, although it's still pretty cool for Earthlings. And yeah, Cassini took advantage of this new unique opportunity. The entire mission tour was redesigned, and many flybys were granted to Cassini. You've seen this artist impression, having close flybys, sampling this plume material, and with that investigate the interior. And that way, actually, only the subsurface ocean was discovered a few years later, after for 5 or 10 years after the discovery of the plumes in 2005 until like at least 2015, there were still many people thinking, no, there's no liquid water. It cannot be. This is a cool to the bone body. We don't know how to create liquid water, how to create this heat. But nowadays it's accepted, and thanks to this measurement. So the two instruments that benefited most from this opportunity are the two mass spectrometers on board Cassini, the ion and neutron mass spectrometer, sampling the gas that is emitted into space, and the cosmic dust analyzer that samples the ice grains. And this is the instrument I was working with for the greater part of my career. And there were a number of findings, and I just summarize the main findings up to 2022 now in the summary slide, and later I go into some detail for the latest findings that were published in 23 and 24. So although the mission ended in the fall of 2017, data analysis is still ongoing and papers are still published up to recently. So yeah, main findings for the inorganics in the ice grains that resemble the makeup of the ocean. Similar to Earth, we have sodium and potassium, salts, chlorides, but in contrast to Earth, we have a very large abundance of carbonates in the ocean. And also an important finding was the nanosilica grains entrained in the ice grains. So the total ocean salinity is somewhat less than Earth probably, and it's much more alkaline due to this high abundance of carbonates in the ocean. Organics are also in the ice grains, two end members. One is low mass, small molecules that have reactive groups like amines or carbonyls. On the other end, we have this macromolecules that also have oxygen and nitrogen bearing functional groups. We were limited here drastically by the capabilities of these instruments, which were never designed to do organic chemistry in an icy on Enceladus, of course. But that's what we could tease out of the data up till now. And in the gas phase, this is the main compounds in addition to water is molecular hydrogen. This is a very puzzling finding. Ammonia, CO2, methane, and also volatile C2 and C3 organics. Whereas these small molecules we find here, and also these low mass molecules, they probably are in the vapor phase, and these ones, they condense basically from the vapor phase onto the ice grains. And by contrast, these macromolecules, they must be solid from the start. And the way they're entrained in the ice grains is probably that we have an organic film floating on top of the water table here. The water rises through the crustal cracks. So the ice shell is just about 3 or 4 kilometers thick here. And the icy crust basically swims on top of the water, and with that, the water column rises through about 90% of the diameter. So the water table is probably just a few hundred meters away from space. And this volatile gases, they bubble from below, this hydrogen, methane, carbon dioxide, and when they burst, they create a spray that on one hand create the salty water droplets, on the other hand throw up solid organic material. That's the hypothesis, which then are entrained in a few of the ice grains because the water vapor condenses on top of this organic cores, and with that we find this macromolecular compounds entrained in ice grains. All right, so what we learned about the ocean floor. So this was like the near surface water analysis. So with the plume, we only probed the uppermost meter or so of the water that stands here in this crustal cracks. But we learned also something about the deeper interior. This finding is of the density of a rocky core is a very significant finding, not done by mass spectrometry. This was a gravity measurement. The higher moments of the gravity field of Enceladus, the series of flybys was measured, and that also confirmed that there's some liquid water layer. But even more importantly, it found that the core is very low density. It's larger than originally thought from its mass, and with that the density is very low, just 2.3 gram per cubic centimeter, which is not consistent with any reasonable form of solid rocky material. So the hypothesis is that the core is not solid. It's porous. Porosity of 10 to 20%, and this is reasonable in a body with such a low gravity. On a larger moon like Europa or Earth moon, gravity would compact any porosity and quench it out, but with a 1% gravity, Earth gravity we have on Enceladus, it allows these porosities to survive, even in the center of the moon. And this will become important later, because the ocean water can, with that, percolate into the core. It just sinks into the core by gravity, and in the core, it's probably heated up by tidal forces and re-enters the ocean as hydrothermal fluids. That's like the motor, the hydrothermal driver of Enceladus. At least that's the most accepted theory. It's not, I wouldn't say it's not generally accepted, but that's the best theory on the market, at least, to explain the hydrothermal regions we have. The hydrothermal temperatures are evident first by the finding of this nanosilica. From this abundance of nanosilica, we inferred relatively mild temperatures at the bottom of the ocean, and independent evidence for this hydrothermal activity also comes from the hydrogen emission, because this hydrogen has to be produced all the time. A small moon like Enceladus cannot store primordial hydrogen. It's totally impossible. So you have to have an efficient mechanism that produces this hydrogen, and the best candidate for that is submethanization, which by itself is an exogenous reaction that also can create locally hydrothermal hotspots. So this is, again, summarizing the idea of water sinking into the core. This is a heat map of this 3D modeling that for the first time suggested this hydrothermal tidal power plant, I call it here, because only with this unconsolidated core, the tidal forces that work and flex the core material can be efficiently converted into heat. If you flex a solid rock, you have to flex it a lot to create heat, but if you have like a sandbag, then you create a lot of friction, and only with that friction, this is the only model that with a given tidal energy can create the heat that is observed and the 30 gigawatt of total power that is needed to maintain the ocean liquid over geological timescales. And the temperatures that are predicted by this model are in the ballpark of 200 degrees in the center, about 100 degrees at the ocean floor, and the ocean itself, of course, is very close to 0 degrees for the greater part. So now to the more recent findings. First, the discovery of phosphates in these ice grains in the E-ring. So up till 2 years ago, of the 6 bioessential elements, the Schnapps elements, phosphorus was the only one that was missing in the Cassini data. All the others have been found in the ice grains or in the gas before. And there was a paper that got quite some attention in 2018 that said, well, yeah, according to our model, phosphorus should be depleted on Enceladus or more general in ocean worlds in general. And yes, maybe you have water and hydrothermal fluids, but if phosphorus is missing, this might be the bottleneck for the emergence of life. So this was an important question, and we were happy when we, in a reanalysis of the Cassini data, found ice grains that have a lot of phosphorus in it. This is a mass spectrum, and these are the 3 main phosphorus-bearing peaks. It's a unique fingerprint of sodium phosphates and sodium hydrogen phosphate. And in addition to this phosphate-bearing peaks, there's also a strong hydroxide peak that gives evidence for the high pHs here from which these ice grains formed. It's a high pH environment from which these ice grains formed. And we used an analog experiment in our labs to reproduce the spectrum to see what ingredients we need to get this spectrometric fingerprint. And I get back to this analog experiment in 10 minutes or so. And And we could, with that, infer the concentrations of phosphates in the Enceladus ocean, and we came up with a number in the ballpark of a few millimole, about 10 millimole or so, and this is much larger for comparison with Earth, where we have just 1 micromole, so it's a factor of 1,000 or so more phosphate. It's really a lot. It's what you use in fertilizers or so. It's a lot of phosphate, and we really scratched our head and well, no one will believe us. So what is the reason for that? And that when we contacted Yasu, and he had already experiments running by chance, and they were further fine-tuned to simulate the conditions on Enceladus. And Yasu at ELSI came up with this kind of reaction, a buffer reaction that could be the driver for the phosphate chemistry in the Enceladus ocean. Something like this. I mean, the apatite calcite buffer system or a similar buffer system can explain this high phosphate abundance in Enceladus. And the reason for that is, or the reason why phosphorus is generally seen as a bottleneck is, one, it's the least abundant cosmochemically of the 6 SNOPs, and 2, it doesn't like to dissolve. So its bioavailability is generally low because it's locked up in rocky material, like this calcium phosphates or magnesium phosphates. They are poorly soluble, except if you put a lot of carbonate into the equation here. And in contrast to Earth ocean, we have a lot of carbonate in Enceladus ocean. And then you drive the reaction towards the right. The calcium then takes the carbonate and releases the phosphate into solution, generally in the form of the sodium phosphates. So this is shown here in this cartoon that came out together with our publication. And this reaction here is, you see in this plot, how the carbonate abundance, so total carbonate including free CO2, correlates with the phosphate abundance. And you see this nice correlation. The more carbonate you put into a system, the more phosphate you can dissolve. And what gives credit to this reaction that Yasu found in his lab is that it really nicely matches the observed CO2 range. That was from previous Cassini data, the total CO2 in the ocean, predicted in the ocean. And you see how nicely matches it the phosphate abundance we observed later in the CDA data. This is another way to plot it. Again, we have the phosphate or dissolved phosphate here. This time we put the pH on the x-axis, and we have 2 cases of high CO2 and low CO2. High CO2, that is what we think we have on Enceladus, but not just on Enceladus, beyond the CO2 snowline. This is generally true not just for Enceladus, but for all bodies that formed outside the CO2 snowline of our solar system. So anything at Saturn or beyond should have similar high CO2 abundances in all ocean worlds there, like Triton or the Uranian moons or Mimas or Titan. They all should have this CO2-rich waters that again then allow high phosphates. And with the pH, Enceladus smack on hits the maximum of this curve between 9 and 11, and with that we get this really high phosphate abundances in the ocean. And this correlation of carbonate and phosphate was reinforced by the Ryugu samples of Hayabusa 2, where very similar sodium phosphate were found as deposits. And the Ryugu parent body is suspected to have formed outside the CO2 snowline. And there's also, I hear, similar sodium phosphates found in the Bennu samples from OSIRIS-REx. And then you could ask for Europa. Europa currently is certainly inside the CO2 snowline. And then it would plot on the lower curve with a pH of around neutral. It would have much lower phosphate in the ocean if this buffer controls the phosphate abundance. But it's still comparable to Earth's seawater, but with a recent finding by James Webb observations that was also published about a year ago of this high concentrated CO2 ices that has to be endogenic to all we know. There seems to be a lot of CO2 coming from below, from the ocean, and with that, this gives rise to the idea that there's maybe more CO2 than we thought in Europa's ocean, and then Europa would also plot up here and allow much higher phosphate concentrations. All right, so the other recent finding was again by a reanalysis of Cassini data, this time of the ionate-neutral gas spectrometer, INMS. It was an AI-aided reanalysis in contrast to all previous analyses that were done just by humans. And the main finding is that they definitely identified hydrogen cyanide in the gas. And this is, of course, a big deal. And the likely presence of these highly reactive acetylene molecules and also alcohols. And yeah, the HCN is important. Most of you will know that it's a really nice precursor for prebiotic or precursor for prebiotic chemistry, because it can play a role in a number of pathways for the formation of nucleobases and amino acids, or directly initiate the synthesis of amino acids together with this ammonia, which we know is also abundant on Enceladus. And both these findings, the phosphates and this HCN and reactive molecules, further increase the astrobiological potential, let's say, of Enceladus. What is puzzling, though, this is now the latest volatile map. After this reanalysis, they also tentatively identified O2, although it's not 100% like the HCN. But still, you have a really wide variety of redox states right in the gas phase, from totally reduced to totally oxidized and everything in between. And specifically, something like HCN doesn't survive in liquid water. It would react within hours. So how does this reside in the ocean? It doesn't make sense that you have such a wide variety of redox states present in a single aquifer, right? So the idea specifically, and that is also given in that paper, that HCN and also possibly the tentative O2 is created here on top of the ice shell. When it's subject to UV radiation, most of the plume material doesn't go into the E-ring. Most of the plume material falls back as snow. So you just deposit all these organic ingredients on top of it, and then you can form HCN by UV radiation. That's a very well-known reaction, and also alcohols. And the O2, you would just form from the ice. You would create H2O2 first, and with that you have something that can oxidize everything. And the nice thing is that this material gets buried, and over geological timescales like 10 million years, it will sink down and will be released into the ocean. So you have an oxygen source probably in this otherwise very reduced ocean, and something like HCN can create disequilibria. And with that, maybe you have a potential other habitat, not just in the hydrothermal vents, but just below the ice shell, where you have access to these molecules that are produced on top of the ice shell. All right, so with that, I come to the end of the Enceladus section, just looking forward. A year ago, ESA now has committed to send a lander to Enceladus. It will still be like 20 years from now, but ESA is slow, but they're on track, and they have committed to it. Studies are ongoing. Science definition teams are assembled as we speak. I think you can still send an application for the science definition team. And also NASA's decadal survey had ranked this Orbilander as a flagship mission. Probably will be delayed due to the funding issues at the moment, but we also have New Frontiers 5 and 6 that are there open for Enceladus plume sampling missions. All right, but more immediate, we have now on their ways JUICE and Clipper, which will reach the Jovian ocean moons 2030, 2031. And specifically, Europa Clipper has this extremely capable latest generation of mass spectrometers, the the predecessors of the Cassini instruments. Mass specs has a mass resolution in excess of 10,000 compared to 100 on INMS, a much wider mass range too. And SUDA is a much better instrument than CDA, and it doesn't need a plume. Of course, if there's a plume on Europa, perfect. SUDA can do a much better job than CDA because this instrument is designed for that. CDA wasn't. But the baseline is like to analyze these ice grains that are knocked off the surface by micrometeoroid impacts. It's an airless body, so it's subject to all these micrometeoroids. And in a close flyby of Cassini, of Europa Clipper, we expect to detect thousands of these ice grains. So we get, with a close flyby, we expect like about 3,000–4,000 spectra, which are, each of them is a surface sample, and we can then map them onto the surface to the landforms. Yeah, this is SUDA now in comparison to CDA. It's much more capable, and this is here a HIVE instrument that we will propose for the future Enceladus missions, which even better mass resolution and mass range. All these instruments work with the principle of impact ionization. So an ice particle hits the bottom of the instrument with kilometer per second, and so the kinetic energy of the impact ionizes a substantial fraction of this particle, typically micron or submicron sized, and then we do time-of-flight mass spectrometry with this impact puff, basically, of the ions that are in this impact cloud. That's the principle. And this is a very hard instrument to calibrate because micron-sized ice grains at 5 kilometers per second are really, really hard to do on Earth. And that's why we use an analog experiment that is much easier to handle, and where we use a very thin liquid beam and intersect it with a pulsed infrared laser, and the wavelength of the infrared laser is tuned in a way that it implants a maximum of energy into the water molecules and heats the water up to thousands of Kelvin within picoseconds and creates a thermal explosion, if you want. And this thermal explosion creates very similar ions, cations and anions, than we get from the impact ionization process. And this is a comparison. This is a CDA spectrum from Cassini, almost pure water ice grain, and we use this Cassini data actually to fine-tune and calibrate our instruments that it can simulate different impact speeds, because the spectral appearance in this kind of measurements is different for different impact speeds. And now what we do in preparation for Clipper and future Enceladus missions is to create a spectrum library with all kinds of inorganic and organic compounds. In the recent years, we focused more and more to biogenic compounds, because that's everyone is asking for that. And for example, now going back to the Enceladus scenario, we know this. I told you about this high mass organics that we find in 1 to 4% of the ice grains. And if there's life on Enceladus, either at hydrothermal vents or further up, it's very likely that, like on Earth, we will have the microbes or the fossils or whatever, dead or alive, it doesn't matter, but it's likely that it will also end up in this film. This is the idea here, and then we try to simulate that. Or first of all, Pereira and Cockle simulated this process, like, okay, let's put some microbes on the top of this beaker and then just evacuate and let it boil at 0 degrees. And they found that with a cell concentration of 700,000 cells per milliliter, about 10% of the aerosols carried cell material. So there isn't a selection effect. We just see 1 to 4%, and then again, there's a selection effect. And if we are more pessimistic, that many people are, for Enceladus, say just 1,000 cells per milliliter, then you would end up with just 1 out of a few thousand ice grains would carry cell material. And this would potentially dilute such a biosignature. Specifically, if you sample the plume material with like a big catcher, you would not just mix the biosignature up with all kinds of other organics and salts, but you would also dilute it a lot. And with this impact ionization detectors, we have the capability to analyze individual ice grains and with that catch them at higher concentrations, and that's what we simulated. We took a microbe, Spingophyxus alescensis. It likes to live in cold waters close to the ices in Alaska here, and put it into a water droplet in our analog experiment. Actually, we choose cell concentrations that are equivalent, that one cell would end up in one of these 15 micrometer size droplets. And we then went down to just 1,000 cell per droplet to see how low we can go. And we were really pleasantly surprised. That was just a shot in the dark, but we were pleasantly surprised that we see a lot of biosignatures with that. So this is a mass spectrum. I cannot go into the details here. It shows water and salts, but there's a lot of biosignatures here. A whole suite of amino acids and metabolites we see in the cation mode. And if we go to the anion mode, above mass 200, we have a clear view onto this nice sequence of fatty acids that there's a clear biosignature. And we are encouraged by that kind of experiment to continue to shoot on microbes. This is a list. What we found, the paper was published half a year ago, and this demonstrated that even if there's just a biomaterial in just one of 10,000 ice grains or so, this instrument could still find it if they fly through a plume, or also with SUDA, if we have some of these materials in the near surface ices. All right, yeah, we're currently making our life harder. This was just a pure water ice, but we now add salts and other organics, and to simulate Europa conditions, we also irradiate these substances to see how they modify, not just biosignatures, but all kinds of organics in the interplay with salts and H2O2. This is what we're currently doing to see how this suppresses or modifies potential biosignatures or just anything organic. Yeah, and with that, this is now my last slide summarizing the ongoing and future work. I said most of this already. We still continue to do Cassini data analysis. So the data set is so large that we now embark to machine learning and AI help to analyze the large CDA data set. We have hundreds of thousands of spectra, and currently we only worked with manpower and only went to like less than 10% of the data set yet. But of course we picked the low-hanging fruits already, and all we have now for the next 20 years probably is James Webb. So, and James Webb has already proved its quality at Europa, and there are more campaigns coming up at Europa, but also in Enceladus, so stay tuned for that. And yeah, thank you for your attention.